yeah, I see it. Got it.
Okay, then. So, welcome everyone to this week's Origins Colloquium. It's a pleasure to welcome Kathy Dukes to give the talk this week. Kathy received her undergraduate degree from University of Michigan and then a graduate degree in engineering physics from University of Virginia. She currently directs the Laboratory for Astrophysics and Surface Physics, LASP, and is a core member of AVICO and the AVICO management team. So she works with a range of NASA and NSF-funded research, including the Apollo 17 mission analysis return. And I think today we'll hear mainly about the OSIRIS-REx mission. So welcome, Kathy. We look forward to your talk.
Thank you, Jonathan. Okay, so I'm Kathy Dukes. I am a research scientist in the material science department here at the University of Virginia. And I am working with a team, graduate students. So one of my graduate students is an astronomy student here, Lianis Reyes-Rosa. Adam Woodson is a research scientist with my group, and Nadira Hudson is our VICO undergraduate who will be continuing this talk, I hope, in a couple of weeks. So I'll be talking about near-surface processes that are occurring on the near-Earth asteroid Bennu. This talk is sort of in three parts. So the first part of the talk is really what is the OSIRIS-REx mission? This is just maybe a review for some of you, but also some of our new data, some of our new findings. The second part of the talk will be about new findings from the Bennu samples concerning space weathering processes on the surface of Bennu. And then the last part of the talk is new preliminary data that we're taking this summer and took maybe in this some of it in the springtime, what we're finding here at UVA. So without further ado, let me see if I can figure out how to advance myself here. Okay. Why does that not work?
Just exit it. Just one click on the presentation, then should work.
You think? Oh yeah, perfect. Experts. Thank you. So this is really just a reminder about what are asteroids. And so asteroids are, of course, large rocky bodies. Asteroids are related as well to comets and to meteorites. They're all part of the same sort of family tree. And so when an asteroid is impacted in the solar system and breaks apart, if it becomes less than about a meter in diameter, then it's termed a meteoroid. And so the meteoroids are floating sort of with the asteroids through space. And if they move in the direction of the Earth and then enter our atmosphere, they become termed meteors. And so when you see a meteoroid entering the atmosphere and then moving through the atmosphere, you see these bright streaks, and that would be a meteor sighting. And then when it lands on Earth, it becomes a meteorite. And so we've had samples of asteroids really since the beginning of our planet that we've been studying and trying to learn something more about the planetary bodies around us. So OSIRIS-REx is NASA's first mission as a sample return. And so the OSIRIS-REx acronym, sort of incorporates the mission's objectives and concepts. So the O is for origins. We're trying to understand the origins of our planetary bodies, our planetary neighbors, near neighbors, particularly carbonaceous asteroids, but also what's on these carbonaceous asteroids. It's thought that they contain some of the building blocks of life, including water and different types of organics. So the return mission is to really try to understand what is in these materials. Additionally, there is an interest in making sure that when we do remote sensing or orbital sensing using optical techniques, that our optical techniques we're interpreting the data correctly and getting the correct mineralogy. So the return of samples provides us with hand samples where we can compare what we actually have in terms of within this material with the spectral interpretations that we're doing. The samples are also for resource identification. Do we have rare earth elements, maybe something like or gold or something additionally worth mining. The understanding the composition of this material also provides helps with the security of the planet so that we can understand what these planetesibles are made of. And then the REx part of the OSIRIS-REx acronym is just sort of the general understanding of the regolith. What is a regolith made of? What are we finding? What is the morphology, the texture, the geochemistry that appears in an asteroid regolith? So this isn't the first time, of course, that NASA or other groups have been to asteroids, right? Both ESA and JAXA and NASA as well have visited asteroids before, but these have been either flyby missions or orbital missions like the Dawn mission to Vesta and Ceres. Hayabusa from the Japanese has returned material to the Earth. Previously from also a carbonaceous asteroid and then a chondritic type asteroid. And then, of course, we've flown by a number of asteroids on our way to other larger planetary targets during the Galileo or Cassini missions. One of the questions that we get a lot is, why did we choose Bennu particularly? And there's 1.3 million asteroids that have been observed in our solar system. And so we need to narrow this down. And one way to do it is, of course, to use practical considerations. How many of these are close to the Earth? And that narrowed the population down to about 7,000. Which of these 7,000, how many could we return with the current methods within a reasonable timeline? That narrowed it to 192 potential targets. And then of these 192, it was important to have something relatively large where you could have an orbiting spacecraft, particularly one that was going to be orbiting close to the planetesimal surface. And the concern was for rotating bodies that you spit rocks and debris from the surface as it orbits due to the low gravity. So something with a larger gravity was important. And so this narrowed the population down to 26 potential targets. Of these 26, 5 were carbon. And one of the targets and the objectives for this mission was really to try to understand, more about where life could have come from. Where are there organics? Where could there potentially be water? These are the constituents of life that could have seeded the Earth. And so we wanted a carbon-rich target. And so this narrowed it down to 5 potential. And then one of them, Bennu, was the most convenient and expedient in terms of telemetry. So the OSIRIS-REx mission then blasted off in 2016, arriving at Bennu in 2018. So it took 2 years to arrive there. And during that time, it was not dormant. We were taking data in order to try to understand what the constituents were on the surface of the planetary body. And so in doing so, we had a number of tools, obviously optical cameras, etc. But we also had a visible infrared spectrometer, the OSIRIS instrument, as well as a higher wavelength instrument, OTES, to look at thermal emission. And these instruments were turned on toward Bennu in order to try to get an idea of what the constituent minerals might be. And so we were trying to find water on the surface. And so one of the things we found immediately, so the Bennu, the spectrum is here. You can see the wavelength range across the bottom here, and about 2.7 indicates a vibrational band for oxygen and hydrogen. And so this would be a hydroxide. This indicates a hydroxide here. You can see some comparative meteoritic material, Avuna, et cetera, CM type meteorites, all having a large band in the same position that generally indicates a large concentration of phyllosilicates. And so we knew going in that we had a target that would probably contain water. Additionally, we looked for organic features. So those tend to be in the regions of 3.5 2 to 3.4 for our target. It's a little bit difficult to see here, but there are some absorption features in this range that one could compare with these hand or remotely sensed samples on the right-hand side. And so you see absorption features here in the sort of 3.4 range or below that might be indicative of the presence of organics in the near surface region. And so arriving at Bennu, we had to find a place to land. It turns out that we didn't have good enough resolution in our optical spectroscopy from Earth in order to figure this out. And it took a while to actually map the surface. And it was surprising to the entire team how many boulders it turns out it's on the surface of this rubble pile. You can see it sort of rotating here, and there are not that many flat spaces. And even though they look like sort of tiny pinpricks here, if you look at the scale bar on the bottom, this is 5 meters. So 5 meters would be maybe 2.5 Jonathans or maybe 3 Jonathans. I'm not really sure, but something like that. And so to find a place to land, we needed at least about a 20-meter diameter that we were pretty certain we could hit. The spacecraft had to hit this target by itself because the signals take too long to go back and forth during the sort of time frame from the Earth to Bennu. So this was an entirely remote descent. And so the sample sites were narrowed down to 4. And then Nightingale was selected based on the sort of physical properties and the likelihood of success. So you can see we're trying to land in the space. This is supposed to be like a little parking lot here. You can see the cars in the parking lot. We're trying to land in the blue circle, avoiding these giant boulders here that are on the order of 5 to 6 meters. Surrounding it and hopefully landing on this fine-grained area here. This region is fairly typical of the surface of Bennu, although slightly less weathered. We were looking for something that would show sort of the native materials as opposed to material that had been processed either by impact or space weathering or other processes. And so descending looked like this. So OSIRIS-REx had an arm for the sample return collection that is on this bottom here. This is called the TAGSEM head. And it was at the end of this leg, and you can see it as it's moving toward the surface, it orients itself. And the idea is as this tags the surface, a puff of nitrogen, high purity nitrogen, then is blown out into the regolith to uplift some dust from the soil. And you can see that, there's more than an uplift. It turns out that the surface was much more porous than we expected. Although we did have some contingency plans, there's like a spring and other mechanisms if the nitrogen failed. But we went about 0.5 meter into the regolith before the thrusters fired to lift the spacecraft back up into orbit. And you can see all of the debris that was collected or that was ejected from the surface during this collection event. We learned some things really just by contact. This is also a new collection method, I should say. Previous methods have been sort of sending a pellet target, shooting that into the asteroid surface and then trying to collect the debris that way. This was very efficient and probably will be used again. So what we found was that this is an extremely, porous. We knew it was a rubble pile asteroid, but the surface is very porous. We collected about 120 grams of material, a little bit more than this, with this method. For comparison, Hayabusa 1, which went to the asteroid Itokawa, collected 60 milligrams. So if you think about an ibuprofen, the active material in that ibuprofen is 200 milligrams. So you can imagine how small a concentration that was. And it's great. We got amazing science from it, but still very small. And so there are a number of things that one can't study. The second mission, the Hayabusa 2 mission, also to a carbonaceous asteroid Ryugu, collected 5.1 grams. So we are, orders more than an order of magnitude more material now has been collected and is available for analysis starting this summer by outside groups. Additionally, in addition to the TAGSEM head, we had on the surface of it something called the contact pads. And the contact pads are these little pads on the exterior. So we have two populations of material that was collected. The interior population, which was the TAGSEM head, this is a general material that was collected. And this is, sort of representative of somewhere in the top half a meter of regolith material. The point of the contact pads outside here is to collect material that was right on the surface. So the idea is, you'll see a picture in a sec, what they look like. The idea was to collect particles that had been exposed to the space environment, things that had been weathered in a way and might be different than the general bulk material. And so you can see the particles that have been collected. So you kind of see these little particles flying in and flying out, mostly flying out from the TAGSEM head. We had so much material, probably about 200 grams, so much material that there's a little mylar flap here that didn't close. And so material was kind of going out as the spacecraft lifted off with the TAGSEM head before it actually got stowed in the sample return capsules shown here on the left-hand side. And so it took about 2 years now after the collection and the stowing of the material for the samples to arrive back on Earth. And this is just kind of a fun shot of how the sample came back to Earth. So OSIRIS-REx flew by the Earth, dropped the sample return capsule. It tumbled through the sky and did not deploy its parachute until very close to the Earth, which caused a lot of sweat. But it slowly then descended into the Utah salt flats here. You can see the capsule itself here with its parachute, the red parachute on the top there. And then the capsule, as we get closer, you can see the PI for the mission, Dante Loretta, is here, and then a number of other people documenting the capsule, etc., which is then carried to a helicopter, taken to Johnson Space Center, where our curation center is for Antarctic meteorites, return samples, and lunar materials. And so that was carried into the Johnson Space Center. There was a waiting, of course, clean room for them, and the sample and the capsule was not opened until it was inside a nitrogen purge glove box, and you can see that here. So this is, just revealing, taking the cover off. There were people there constantly, pictures being taken, media. It was quite the event. So the samples are inside this nitrogen glove box. There are a number of glove ports here. This looks sort of like an exciting job, but it turns out that, in order to work with these samples, you are standing up for hours at a time. It's cool inside the clean room in order to preserve any type of chemistry, not to change things. And you are always pushing against the pressure of the gloves in the glove box as you use tiny little tools to try to scrape small samples into vials, etc. So it is quite a procedure. Eventually, the entire return capsule was disassembled, and it took some time. I'm sure you guys heard that there were a couple of screws that were difficult to get off. They had to remake some tools and to put tools into the glove box. You can only use very specific materials, etc., in order not to contaminate the sample. And so that took some time to develop and remake the tools in order to get those screws off. But when the top was opened, this is what we saw. And you see lots and lots of material of different sizes, dark, maybe a few light pieces, etc. Inside. Additionally, I didn't want to leave you hanging here on the contact pad story. So these are the contact pads when they have arrived back to Earth. This is important for us because we're part of the contact pad sample analysis group. And our interests are in space weathering and surface processes. And so we are currently looking at the general regolith material, but we'll be collecting the contact pad material shortly. So you can see there's 24 contact pads here. This is what they look like up close. All of this is in the glove box. So these images are taken through the glove box in order to try to identify whether or not we were successful in capturing particles from the surface. And we knew that there should be particles because you could see them with the cameras on the spacecraft when it was before it enclosed the tagsum head in the sample return capsule. And so we had a couple of months where we were sort of desperately trying to search and figure out where these particles are. It turns out with the lighting that we had that you can see all of the solder around the outside is shiny, but we were hoping to see particles trapped either in the loops or in the weave, deeper in the weave here, of these stainless steel Velcro pads. So I don't know if you can see, probably it's difficult. It's difficult anyway, but around the green, you see this little gray particle in here that's on the order of a millimeter in size. There's another one particle here trapped between two sort of loops. And so we had a number of us going through 24 of these, searching desperately for particles and circling them and trying to come up with, locations that we thought were consistent and believable. Those samples we'll get back to. So the general aggregate material is shown here. So first on the left-hand side are images that were taken at Bennu from the orbiter. And so we took a lot of images of the topography and to try to understand the petrology and the geology of the planetary surface. And when we looked at the different types of boulders and materials on the surface, they were sort of generally falling into one of three categories. So at the surface, what you see are, sort of bumpy looking, hummocky type boulders. So these are things that have a lot of topography on them. We also saw things that were flatter, that had these sort of cleavage planes. We called these the angular rocks. And then at the bottom, you see rocks that have different types of veins or different compositions. And these are called mottled because of their sort of mottled in color appearance. So when the samples were returned to Earth, we tried to figure out what particles were sort of the children of these parent boulders. And so I note that while things kind of look similar, the scale bar on the left-hand side for the boulders on the surface of the planet are in meters, right? And the samples that we have collected are in millimeters. So these are very small fragments. But generally, we saw, sort of the same petrology and topography. We see things that look hummocky and bumpy and sort of rounded in places, materials that may be related to the hummocky surface boulders. There are the angular grains, similar to the angular grains here, and then the mottled material. And this is the heart of Bennu, which was one of the first samples that was analyzed. And you can see the different colors and compositions here. So we saw
maybe about 10 minutes, Kathy, if that's okay.
Yep, that's okay. So I'm going to kind of whip through this, but here's the general composition of things that we found are indicative of what we expected. So we do see using a bunch of different techniques, a bunch being all electron microscopy, optical methods, organic methods, different types of spectroscopy. We see phyllosilicates. You can see how they are formed here, the mineralogy. These are electron microscope images, magnetite, pyrrhotite, dolomite, calcite, a range of organic species, including amino acids, all the biogenic amino acids, etc. And then all of these minerals are telling us that this is a wet surface or was a wet surface and contains organics. The next thing we started looking at, and this is a topic that is of interest to us particularly, we're interested in how this the space exposure to space changes the surface. And you can see that this has been observed for many, many, many years, right? We see on the surface of the moon, you can see the cratering here, and you can see the different coloring on the surface. You can see that it's brighter toward the center of the crater and then darker around the edges. We see something similar, although not identical. In fact, it's sort of inverted before and after we blasted off of Bennu. So this is before we hit the surface of Bennu, and then this was observed after the tag event, and you can see the color change there. And so one of the questions has been, what is this color change coming from? And so it had been known that the sun produces radiation and ions and is continually interacting with the surface. And so experiments were done, these were done in the 60s, where different types of minerals thought to be composed of minerals considered to be lunar, were irradiated with protons, and you can see the darkening here. You can see spectrally, you see it visually. Spectrally, we see this absorption feature attenuating, darkening, and a little change in the slope. And so we knew that there were these changes that were happening, but we didn't really know why or how. And so it wasn't until we developed sort of more sophisticated instrumentation in the 70s and 80s that we were able to really understand what was happening. And so it turns out that in the lunar case, there is with ion impact and also meteoritic impact, the formation of these little iron nanoparticles that darken the surface, that attenuate the surface. You can see this with other methods. This is an optical method. You see the same thing with ion fluence. And you see a change in the reddening of the surface as you form these iron nanoparticles. So we just finished analyzing the surface. Some of these are tagsum head particles, and some of these are contact pad particles. But here we are looking at space weathering effects. And so what we're finding is that space, in fact, there has been space weathering on the surface of Bennu. And so what we see here are impact craters created by small micrometeorites. We see splashes where the micrometeorites impact the surface and then heat up and melt, and so creating these little splashes. We see all kinds of interesting features. We see the formation of these little whiskers on the surface of sort of sulfide melts on the surface where you have an impact, and then they form these little, and the fingers also have a different composition than the host material. We see other evidence for space weathering, including the solar wind damaged rim. The solar wind is typically protons and helium of a particular energy, and so the depth at which these ions can penetrate is generally relatively uniform. So it creates the sort of rim on the surface of everything. In addition to that, you see these little big tracks here. These are from energetic particles from the sun, and counting the density, determining what the density is of these tracks can give you some indication as to the exposure age of that particular particle. In this case, this was 45,000 years that this had been on the surface of Bennu. Additionally, we see other changes. We see the formation of these vesicles. We see chemical changes, the formation of a nitride on the surface of some of this material. So these are just smaller insets of this larger image on the top. And we can see that this is a crystalline. It's not just amorphous. It's not just glassy melt, but that it has been processed further to create sort of a crystalline cladding on the surface. So at UVA, we've been also studying the surfaces using a technique called X-ray photoelectron spectroscopy. If you were on the tour 2 weeks ago or last week, that was my stop. And so this is a method that uses X-rays in order to determine the composition and chemistry of the near surface region. So the near surface region is about 10 nanometers thick. That's, I don't know, between 10 and 20 atoms, depending on the material. And so we're really looking at the surface of these grains. Other reasons one might want to use this particular method for analysis is that it's non-destructive. You don't need to do any kind of preparation. It's quantitative, etc. And so our role in the OSIRIS-REx mission was as a science collaborator doing surface analysis on these particles. And so last summer, our VICO students, Annabelle and Jackson, went with me to Johnson Space Center to collect our material. Because we're looking at the surface, we wanted to make sure that it was not exposed to Earth's atmosphere, because that changes the surface chemistry in the oxidation state. So we had developed this little vacuum transfer vessel here on the left-hand side. You see it inside the nitrogen glove box, outgassing here. And our samples were put on top of our sample platen, which was installed then in our sample vacuum vessel. And then this was pumped down on this little cart that Jackson and Annabelle are working on, brought to UVA. And then subsequently, you can see Lianis here putting the samples into our XBS instrument. So what do we see? So on the surface of these particles, we see, generally similar elements, concentrations to what they see in the bulk, but not exactly. We see high concentrations of oxygen from the silicates, the carbonates, the phosphates, etc. Some carbon, silicon, a fair amount of sulfur in both sulfides and sulfates. And so we're doing this analysis for all of the grains so that we can see just what is the homogeneity or heterogeneity of the material. And you can kind of see our findings here. Some particles have strong sulfur signals. There are a few that's correlated with the sodium. And so we find that the near surface composition is generally homogeneous and comparable to the bulk content, except that they seem to contain lower carbon and oxygen than we had seen previously in meteoritic samples. Probably due to the non-exposure to atmosphere. We've been looking at the composition as a function of depth, and then we'll be modeling this. And then we're also looking at the chemistry, changing the energy resolution constraints of our instrument. We can tell whether the sulfur on the surface is chemically a sulfate, or whether it might be a sulfide. I'm sorry that these are kind of hard to see, but we see in a number of particles that the sample surface has been preserved as a sulfide, but there are other surfaces like the CN here where it's predominantly a sulfate. And we know, because all of these samples were processed in the same way, that this must be endogenous to the planetary surface. And so what is this telling us at this moment? The formation of sulfate is consistent with the formation of salts by different types of evaporative processes. So, ponds inside the planetary parent body that were evaporated over time, leaving behind these types of salts. And so I will pretty much leave you with that. I think I've run through most of these findings, but Nadira will be talking about further results next week or the following week at the VICO Symposium. So thank you. Thank you.
Great, thank you very much. there's plenty of time for questions and discussion, and so maybe Shazreen can help me on that side.
Sounds good.
Yeah, so let's try and organize a little bit then. So perhaps you can just remind us, Kathy, what are the physical properties that sort of, for example, the range of temperatures on the surface of Bennu, and then the history and origin of Bennu. It's something that we think has been around since the beginning of the solar system, do we?
Yes. So it is a carbonaceous asteroid, and it should be made of primitive materials. So it has not been differentiated in any particular way. So that means the thermal processing has been minimal. I think at this moment, people are thinking that the temperature, the temperature currently, this is a rubble pile. So Bennu originally formed probably beyond the asteroid belt. There's evidence for ammonia deposition. We see that we actually see the liquid that and the residual salts inside different vesicles inside the material. So we see evidence for ammonia, and there's a fair amount of ammonia also in the organics that's been observed. So we think it formed beyond the asteroid belt, was impacted, and then during the impact, after the impact, then reformed somewhere in the near, somewhere around 1 AU, and then reformed as a rubble pile. So the current temperature is, similar to the moon or the Earth. It goes from about, there are probably permanently shadowed regions that would be less than 100 K, and probably the highest temperature currently is 400 K. But during its parent body, the internal processing temperatures were something less than probably 100.
Well, you mentioned a surface weathering age of 45,000 years, which just struck me as being quite short. But
it's
perhaps
very short.
Perhaps you can comment a little bit why it's not giga years, or why is it 45,000 years?
So there's sort of two types of ages. So you can have the age of the regolith particles. The age of the regolith particles are greater than 3 billion years, probably 4 billion years old. So they're in that time range. So that would be the general particle. The number that I was quoting was how long that particle had been exposed to the surface of Bennu in its current location, and that's 45,000 years. And that's measured from the cosmic ray tracks. The ages have been measured by isotopic methods.
Can I ask, so the 45,000 years then, does that indicate some impact 45,000 years ago that brings that to the surface?
It could be, or it could be, there's a lot of regolith gardening on the surface. We saw that with the particles spitting. So you can imagine that, maybe there is some type of ice that just warms up and then sublimates. And as it sublimates, everything in its way to the surface can sort of create a small cryovolcano, right? And then redeposit on the surface. So it could even be, it doesn't have to be that it was subsurface, but that this particular grain just rotated in some way.
So there is outgassing from Bennu generally?
We think so. So there was not a spectrometer, a mass spectrometer on the instrument, in the instrument suite. So there's not really a way to know that from the orbital measurements, but we do see, rocks spontaneously moving and sort of spitting, and that was the theory.
All about
yes,
the question.
I also had a question regarding the kind of, or related to the outgassing parts. What's the orbital period of Bennu again? I forgot. Since how often did it come close-ish to the sun to have quite some significant outbursts?
So it's basically at 1 AU. It's basically in an Earth-like orbit. So it's not an elliptical orbit. It's a semicircular orbit.
Oh, right.
And so it's just sort of rotating and tumbling warming and sort of cooling, as the Earth.
So you think there's liquid water in there now?
So the answer is probably no, probably not, because it's just too porous. But we do see liquid water, with other constituents, CO2 and ammonia, in very small vesicles inside the rock. So if you do atomographic imaging, so like a tomography that you might do at the hospital, you can do that with rocks as well. And you can look for pores and small openings. And then with an electron microscope, you can go in and you can do a thin section sort of around those vesicles, and look inside. And they do see ice inside it that is presumably primordial.
So there is water ice.
Yeah.
But the temperature ranges are, you said 400 Kelvin.
Yep.
So.
Right, but it's trapped.
Yeah.
This is trapped right inside of core. It's not open to the surface, and so I think in general right now the thought is that there were aqueous veins in the parent body, right? But for the most part, they were internal. They were not exposed to the surface. So they were occasionally, when you would get a fissure, then it would evaporate or sublimate.
Well, if there are questions in Virginia there, please you should go around the room and take the questions.
Kristen?
Yeah, I have loads.
Great.
It's really interesting. So forgive me, I don't really know what rubber pile is. You kind of explained it already in terms of how you expect it to form. But when it coalesced again, did it sort of all just come together and gently stick together, or were the collisions pretty violent? Like you talk about it being porous. What level of porosity should I be imagining?
That's a great question. So presumably it's both. You have both collisions. We don't see any agglutinate materials, so that's kind of what you see on the lunar surface, right? Where you see really sticky, glassy material created by high energy impacts. We don't see that. So that leads us to believe that that it was a fairly gentle process. Where you had this aggregating, sticking, you could imagine it shakes up all the, maybe the fines go toward the outside, or maybe the fines go toward the inside, I don't know. And you do have this sort of continual raining of micrometeorites on the surface. So you do have these continual impacts, as you could see from the splashes previously. But there is a porosity measurement. I'm sorry, I don't remember what it is off the top of my head.
That's all right. And so then the different kinds of rocks you see.
Yep.
Are they like homogeneously distributed around Bennu, or is it certain collections of, I forget what the humming rocks in one.
Yeah, the humming. So basically, they're fairly. It's heterogeneous, right? So you may have in different regions a little bit more. I'm trying to find the rocks here. You may have some more of one type in one region than the other, but it's pretty uniform. It's not like there was some type of geophysical processing that put these here,
right.
And then the other ones were somewhere else. It really does look like you had an impact and an aggregation thing. All of the material was sort of spinning in space and slowly, gently coalesced. As gentle as that could be. Okay.
We have a question here in the Chalmers that maybe we can go to all of it.
Yeah, I can also ask hundreds of questions, but one special one would be about the presence of water in different states. Like you have the water ice and you have the phyllosilicates and some other hydrated minerals. If one just looks at like all of the results in total, like how much of the water is actually in the rocks than in water ice, for example? What's the ratio there?
So I don't know the ratio off the top of my head. However, it's predominantly the rock material. The intrinsic or inherent ice population is really small. We're talking about nanometer-sized pores that contain a tiny amount of water. So the total concentration of sort of water that they think is in Bennu currently that we're observing is on the order of 1%, which is pretty high, but it's mostly hydroxides in the phyllosilicates.
Yeah.
Yeah.
Which goes towards the formation of phyllosilicates in the protoplanetary disk probably already. So that's actually good to hear. And then another question I would have for the carbohydrates, are there any found, and to what complexity do they go? If you know any of that.
So I know very little about the organic species. I know that they have observed a huge pantheon of amino acids, their amines, etc. There is insoluble and soluble organic matter, just sort of generally identified as well, polyols, etc. I don't know too many details. That's work being done at Goddard by Danny Glavin and his group, or led by Danny Glavin. So the hydrocarbons, particularly, I can't say too much more than that. They do seem to be relatively complex. They have looked at the racemization of the different types of amino acids, looking for asymmetries or enantiomeric excesses that had been observed previously in meteorites. The Japanese mission to Ryugu, which returned carbonaceous asteroid material previously, did not find any difference in left-handed or right-handed amino acid content. And within error, that's what we're finding as well with Bennu.
And just to complete the story there, the deuteration levels or any other isotope ratios, do you happen to know if they've been measured?
So the answer is yes, they have been measured. Sadly, I don't know what they are. That's sort of outside my field of expertise. But the papers are really starting to come out now. It took a while for the sample, we didn't get our sample back until the late 2023, and samples for the first look team were not distributed until sort of 2024 when we were able to remove the head. So it's only been about 2 years. And so the first year, there was a lot of analyses, a lot of sample sharing, et cetera. So the papers are starting to come out. And I think those numbers should be in one of the 2025 papers, if not in the 2024 paper.
So I think there are more questions in Virginia.
I'm just wondering, 2 questions.
Sure.
You showed that there were some micrometeorite impacts. Just wondering how many did you find of those, and if you were able to model the size and the velocities of those particles?
So that's a great question. The answer is yes. So this paper should come out. It's been accepted in Nature Geoscience last month, and so it should come out probably in August. There were almost 200 impact craters on the grains. I think there were only 4 grains in this particular paper that were the contact pad grains. So there was a significantly greater distribution of micrometeorite impact cratering on those. The general regolith, it was much lower. Only about 20% of the grains, between 10 and 20% of the grains, showed these micrometeorite impacts, or at least that we could find. So have we looked at generally the velocity is relatively low. I don't remember what the numbers are off the top of my head, at least in terms of, meteorite size. So you could look at this, right, and say, well, you have an impact crater that's a micron. So they're really nanoscale particles for the most part. And the velocity is tens of, maybe not even tens of kilometers per second. Nathan?
Yeah, I had a question about the leaf boulders that you showed. Some of them were angular. I was wondering,
I tried to find it.
I was wondering how you form this kind of objects without melting or differentiation.
Can you say that one more time, just really loud?
Yes, I was wondering about the angular boulder that you showed.
Mhm.
I was wondering how you can form this kind of objects without melting.
So that's a great question. Presumably, it could be pressure, right? So you could have, perhaps in the parent body, there is some compression. It could be also temperature. As it moves around the sun, you heat, you cool, and you create fracture surfaces, and eventually it fractures. Or it could be, you have an impact at the surface, and it propagates the shock down through the surface, creating cracks or fissures, etc. And that rock eventually populates the surface. That would be my best guess.
I have a question about the composition. So Bennu is carbon rich, but when you showed that there's a lot of oxygen. So how do they decide what's the?
So the carbon content is between 4 and 5 weight %. So it's carbon rich for an asteroid.
Oh, I see. Okay.
But yeah, so
Okay.
it is considered a carbonaceous asteroid. All of these are, but carbon rich doesn't mean it's
that this
just
doesn't-
dominated. I mean, there are other types of carbons as well, right? There are the silicon carbide grains from the solar nebula, etc. But most of the carbon here is in the carbonate materials, and then in just this other sort of messy black material that is just sort of hydrocarbon pH type material.
Can I ask a question? If Bennu was to crash into the Earth, do we have a sense of what kind of material would survive to the surface? And do we have examples of meteorites on the in our collections which are very similar then? And by studying now, we've got Bennu. Can we get a sense of how much the Earth samples have been contaminated, or things like this?
So the answer is yes. There are hand samples. So these one of the first things that the team did was to try to compare these particular return samples from Bennu with our meteorite collection. We already knew from remote sensing that obviously it was carbonaceous, probably similar to a carbonaceous meteorite, but we didn't know which type. And actually, we originally thought it might be an ungrouped type of carbonaceous meteorite, like the Tagish-like meteorite, which contains a little bit more carbon. In the end, these look very much like CI meteorites, which means that they have a composition that's generally solar, except for maybe the carbon, except for the organics and things that are very volatile. So we could use CI, depending on what you were thinking to do. CI meteorites would be the best analog and are very similar. In terms of impact with the Earth, it's a rubble pile, and so I think that at least the thinking is if that ever came close to the Earth, it might be dissipated and fragmented as it entered the Earth. Of course, that doesn't mean enter the Earth's atmosphere, but of course that doesn't mean it's necessarily some of the material might also land on Earth. I think that what we learned is, we've been following its trajectory. It was had the potential for a collision course with the Earth, and I think right now the thinking is that it's very unlikely to hit the Earth. That we're definitely safe from Bennu.
John,
I have a question that might not be well posed, but I'm interested in the space weathering, and you did a lot of experiment. I wonder the time scale and also how much you show that the optical property changed after the space weathering.
So we've been doing experiments on Earth, and so basically the way we try to get a time scale for space weathering events is to, on Earth, take a similar mineral and we look at the response of that mineral to ions, in this particular case to ions, but also to meteorites. So we simulate meteoritic interactions as well. And we look at the changes as a function of ion fluence. And we know basically the solar flux of ions. We know generally what their composition is. And so we can make inferences about how much time on a planetary body, depending on where it is in the solar system, how likely it is to have been, or how long it would have taken to create a particular type of space weathering signature. And so you can see these experiments here. This is a fluence. One can correlate this fluence to time at 1 AU or time at 3 AU or wherever you wish to be. And so that would give you an idea of how long it might take to affect some of these changes. And similarly, the attenuation band of, this is olivine particularly, so how long it takes to attenuate the olivine band to some particular level, et cetera. And so people have considered using space weathering as a potential tool to determine how old a surface might be on a planetary body, but it's complicated. Different materials react at different rates, et cetera, and you have different features. So on the moon and S-type asteroids, iron-containing planetary surfaces or minerals, you get a lot of nanoparticle iron content, but let me see, where was this? But you can see on like C group asteroids, right? Like Bennu or Ryugu, the response is different. And our thinking is that this is actually the formation of sulfide nanoparticles rather than iron nanoparticles. These are sort of generally less iron rich, have fewer mafic minerals in the surface region, and they have a different response. The surface blues rather than reddens. They brighten rather than darken, and so it is a complicated process.
And the percentage of the changes is only very low. Like
the percentage can be low, and it's only affecting, well, each process affects a different information depth, right? So the ions are affecting, maybe 100 nanometers or less. So it's really just a rind around the surface of the grain, and the impact depends, of course, on the size of the impactor.
We're getting close to the hour here, so maybe last couple of questions if there are still more.
Can I continue just to ask a follow-up?
Sure. Yeah, you can ask me.
So I don't know whether this can be applied to protoplanetary disk. You have at the surface, you have small particle like sub-micron size particles, and if they are constantly being irradiated by the star, whether you can tell the difference, like from the different type of stars, you have different kind of space weathering, and consequently you have different.
So the answer is probably that is happening, right? You see the sort of a T-Tauri, right? Sort of radiation during the early protoplanetary disk, and things were irradiated. And so you may get these optical changes, but of course there's nobody there to measure it. As well as, these changes also produce chemistry radiolysis. So you get new chemical species as well.
Meaning that later on, like now, we look at it at different asteroids and see whether we could tell like what this.
Probably not, because asteroids are reprocessed anyway. But like from looking at different protoplanetary disks at different stages and around different whole stars, I don't know.
Yeah. It may be tough to do that remotely, but if there's a way to do it, we should think about it.
Think about it.
Yeah. Okay, then I think we should probably close the main session here. But of course, if you're there with Kathy, you can continue some follow-up. So let's thank Kathy again for a great talk and discussion.